Here we go. We're doing chapter 25, which is chi-square independence test. Okay, this is the last hypothesis test that we will learn. Now, just as a really quick thing, as far as your projects are concerned, okay? So, some people weren't here, but the people who were here and collected information on the election, what I'm going to want you to do is I'm going to want you to come up with a confidence interval and a hypothesis test. You can take, who has later? Well, you can compare, just tell me who you compare it to. So you did it on Mitt Romney, correct? Yeah. Did anybody do it on Mia Love? Oh, you did it on Mia Love too?
Yeah, we did it on all 4 triennial districts.
Oh, you did?
Yeah.
Oh, you only needed to pick. Oh, that's cool.
Just for fun.
Just for fun. That's good practice. So basically, what about this group? What did you guys do it on? Oh, it was the boys and the girls, huh? What did you just do Romney or did you do? Yeah. Okay, that's what I thought. Romney's the only one that I care about. But if you want to do the others for practice, that's good. So number one, you need to do a hypothesis test and tell me if your poll results matched the actual election. So find out the election results and do that. Number two, you need to do a confidence interval, okay, on the same thing. Based on your data that you collected, did Mitt Romney get, did your data, was it within the margin of error? Was the actual vote within the margin of error of your survey that you did? Okay, yes? I know, and that's what I got to figure out. I need to figure something out. So for the people who aren't here, the people who aren't here are in the other group. Yeah. And so, okay. So now another thing that we're going to do, you guys will like this hypothesis test, okay? I want you to either take, let's just pick M&Ms, okay? We're going to do a chi-square test of independence. I don't want you to get those little bags because they're too small for the test. I want you to get a nice big bag, like not the kind that you, as you're going through the grocery counter, the fun size. No, that's too small.
Family size that you can reseal?
It's got to be bigger than fun size. If you want to get the one that you can reseal, that's great. Okay, I don't care if you seal it or not. But here's what we're going to do: is we're going to do a test. I want you to get 2 types of M&Ms. So you can get plain and peanut, or you can get pretzel and whatever. I don't care. But the idea here is we want to see if the color distribution, if there's a difference between, let's say, plain and peanut, or peanut butter and pretzel, or whatever. Just 2 different kinds. Okay. Don't eat the M&Ms until you've counted them. Okay.
Wait, when do we have conference?
After Thanksgiving. So I'm just going to give you it. But today's lecture that we're going to do is going to help you to do this project. Now, there won't be a confidence interval because there's no confidence interval for the chi-square test. So you don't have to do that. We are going to do a test of independence.
So we're doing 2 projects.
No, we're doing 4, I think. I got to figure out what the other 2 are.
Can you make a
Well, 4, no, it's 1 project. You're just doing 4 different samples.
You just keep throwing stuff out to
I
us.
know.
It's
I know.
always keeps you on your toes.
See, now you're like, I wish I could have done that test.
When is this M&M thing due?
Probably the last week of class. I'm going to have you guys create a PowerPoint presentation. I also need to come up with something, so I'll come up with something for the other. So there's going to be another project, probably a grocery store project where you're going to compare some grocery item.
Wait, so next week will be our last test, and then we just have projects?
No, we have the finals.
Oh, I just thought it was 2 things. Okay.
A final too.
See?
I thought our project was our final.
No.
You said it was.
You for sure said it was.
No, I said, do you want 4 tests or 3? And you all said 3, and so this was replacing the last test.
Pretty sure you said.
But it's not a final. Go check the video. I'm recording the lecture right now. Yeah, you guys are making up stuff. It's on the video. I said I normally have 4 tests. We're only going to do 3, and then we're going to do a final project. I probably said a final project, but that's not a final exam.
I think it's been too confusing. We might just have to throw out the test.
So this is a dictatorship, not a democracy,
Why don't we
and
take
this
a
is what we're doing. Okay? All right. It'll be a fun. We need to finish this. Okay? All right. So here's what I want you to do. For those of you who have a computer, you don't need one. It would be nice if the library would let us back in. But here's what we're going to do. Go ahead and open up Excel. And if you don't, we're recording this, and you can watch this later.
There's screens now.
Oh, the screen's not on. Thank you. Okay, so now I'm going to start sharing my screen. All right. So most of this lecture is going to be on Excel today. Okay? All right, so this is a fake data based on a true life thing that happened. Let's say a university offers 2-degree programs, engineering and English. Admission is competitive, and women expect discrimination. Don't you? Tough being a woman, right? All right. Is it fair to conclude discrimination? Okay. So I'm going to give you some raw data, and I want you guys to figure out what to do with it. We got males, we got females, we got admit, we got deny. 35 males were admitted, 45 were denied. 20 females were admitted, 40 were denied. And let's make a nice little box out of that. Okay? All right, so you're the statistician. Can you think of anything to do, like a simple calculation, that could help you decide if there was discrimination going on? Jordan?
Do like a proportion.
We could do a proportion, right? Okay. So in order to do a proportion, what do we need? How do you calculate your proportion?
Do 35.
35 over 45, but there's not 45 people.
35 over.
You need the total, right? Okay, so we need the totals. So we're going to add up these totals. We've got 80 men that were admitted, or that applied. And we got 60 women that applied. And if I add that up, that's 140 people. Okay? So if we wanted to do the percent admitted, okay, how would I do that again, Jordan?
We do the amount admitted.
So 35 divided by 80 works out to be about 43%. And 20 divided by 60 works out to be 33% gentry. What do you think? Is there just some discrimination going on?
Yes.
Sure looks like it, right? 10-point difference. Who's ready to file a lawsuit? Who's with me? Come on, girl power. Okay, it looks like some discrimination's going on, right? However, that was way too simple of a calculation for this class, right? We got to do something much more complicated. Okay, so what are we going to do?
We're gonna use the chi-square
A
test.
hypothesis test, right? Okay, so step number one is what?
Important numbers.
The important numbers. I think we've done most of them. The only thing we didn't do is we didn't see how many were admitted, right? Let's add the totals in here. If I add, oh, now by the way, here, watch something here, okay? As you watch closely. Notice it's adding up the row, which is what I want. Notice it's adding up the row again, which is what I want. Pretend that 140 wasn't there for a minute. And I thought it was adding up the row, and what did it add? The column. Now in this case it doesn't matter, but in a larger table it would. And if you're not paying attention, you'll get that wrong. In this case, it doesn't matter, but in other cases, it will. So just pay attention to that, okay? All right, so the important numbers are done. Step number 2 is what? Categorical, quantitative, or regression. Oh, you don't ask that one. You just say categorical or quantitative. Sorry. I went into Math 2040 mode. Okay, categorical or quantitative? Categorical, and the categories are? No, those are the groups. Admits and denied. Okay, those are your categories, admit and deny. Males and females are your groups. Okay? Step number 3 is the null and the alternative hypothesis. Okay? All right, I'm going to give this one to you because this one breaks the rule. Okay? By the way, let's just review really quickly what is the rules for the null hypothesis.
They almost always have an equal sign.
Almost always have an equal sign. That's the rule we're going to break.
Oh,
What is another rule?
it's usually not stated in.
It's usually not stated the problem. That we'll keep that rule. It's another rule. It's always about the population. We'll keep that rule. What's the 4th rule? What'd you say? No change, no difference, or I should add on there, it's independent. Okay. So the rule is on this one. This is the rule breaker. What we're going to do is we're going to say gender is independent of admit rate. Okay. So the main thing to remember is the word independence. We're doing a chi-square test of independence. Independence should be in your hypothesis. Okay, so this is the one rule, the one case where you can write it out with a sentence or a phrase. Okay.
So instead of like mu, it's.
Instead of mu
whatever
equals
it is.
or p equals, you can actually write out a statement here.
Okay.
So that's the rule we're breaking. Okay. So what's the alternative hypothesis? Now that you know that. What do you think, Kristen?
Gender is dependent.
Dependent. Okay. And a lot of people make that mistake. It's a good guess, though. But statisticians are super anal and weird, and so we don't want to say it's dependent. We want to say it's not independent. Because to say it was dependent would mean there was something biological. Okay? Like, can men have babies? No, that's dependent on your gender, right? There's a physical, biological thing. But there's nothing physical or biological that's keeping these women out of the engineering program at this school, or the English program, right? Okay? And so statisticians are super anal, so rather than saying dependent, we're going to say they're not independent. Because there's also could be some lurking variables. Well, maybe all the women are from someplace. They're from the north, and the men are from the south, and I don't know, could be something else, okay? All right, so there could be confounding going on. So yeah, so that one is so independent versus not independent. Those are the two things that you should remember along with whatever you're comparing, okay? Step number 4 is nope.
Oh, pick a test.
Pick the test. Okay. So, is it z, a t, or a chi-square?
So my guess is chi-square.
My guess is chi-square because that's what we're learning today. Okay, that was a good guess. Yes, it is a chi-square test. Now, how do you tell this is a chi-square test? Okay, it's in a table. You're going to find a table like this.
Will they'll always have a table?
You will always have a table, some sort of a table. It's probably going to be bigger than this, but yeah. Okay, so we're going to call this the observed table. Okay? All right, now I'm going to give you a couple of new equations that you're going to need to know. Okay, so first thing you should do before I do that is go ahead and take your original table that I gave you, and we're going to copy and we're going to paste it, and I'm going to erase the numbers this time, and we're going to copy it again, and we're going to paste it again. Okay? This second table we're going to call the expected table. And then the third table we're going to call the chi-square table. Okay? All right, so I'm going to write this on the board so you can see what the equations are. Okay? So there's two things that you're going to need to do. Okay? Number one, let's say that you have a 3 by 3 table rather than a 2 by 2. Okay? So in this case, I'm going to label this row 1, column 1. Row 1, column 2, row 1, column 3. This is row 2, column 1, row 2, column 2, row 2, column 3, row 3, column 1, row 3, column 2, row 3, column 3. Does that make sense how I've labeled it? Okay? Okay, so the equation I'm going to do is I'm going to highlight this one here, okay? Wherever you are on the table, you're going to have to do this, okay? So this is for the expected values. Expected, okay? So your expected for row 1, column 1 equals your row 1 total times your column 1 total divided by the grand total. Okay? So that's your expected value formula, but this you're going to have to adjust this depending on where you are on the table. Okay? So let me show you how this works. Okay? So here we go. Okay, so this is my expected table. Where's my cursor? I'm in row 1, column 1, right? Okay? So when I'm doing this, you're going to start with an equals. I'm going to do the row 1 total times the column 1 total divided by the grand total. Okay? Does that make sense? Now I'm in row 2, column 1. I'm going to do the row 2 total times the column 1 total divided by the grand total. Okay? Now I'm in row 1, column 2. I'm going to do the row 1 total times the column 2 total divided by the grand total. Okay? And now I'm in row 2, column 2. I'm going to do the row 2 total times the column 2 total divided by the grand total. Does that make sense? Okay, so let's look at this for just a moment. Okay? The idea here is we've just created our null hypothesis here. If there was no discrimination going on, this is what we would have expected. Okay? We would have expected 31.5 men to be admitted, but there were 35 men who were admitted. So more men got admitted than we would have expected. Okay? Let's look at this number here. If there was no discrimination going on, we would have expected 23.5 women to be admitted. Only 20 women were admitted, so it looks like 3 fewer women were admitted. So it looks like fewer women and more men are being admitted, right? Okay, and you can keep doing that with the other ones. So it still looks like there might be some discrimination going on. Now, I don't know about you, but I don't know very many colleges that only have 55 people in them, or 140 people that apply. It's certainly not UVU, right? So this is kind of a small sample size, but it looks like still there might be some discrimination going on. Okay, so that's your table number 2. Okay, that's your expected table. Now we're going to work on our chi-squared table, and I've got a new formula for you. Okay, now Okay, here we go. So the Greek letter chi, it looks like a script X, okay? It's Greek, it's not Chinese. Don't call it the chi-square. It's a chi-square distribution because it's Greek, okay? Chi, and it's also squared. It looks like x squared. If you want to put x on your... So more than likely, this is probably going to be a computer type question because there's a lot of calculations going on. So the chi-squared distribution equals the sum of the observed minus the expected squared divided by the expected. Okay? Now we have, this is a new distribution. We haven't talked about the chi-square distribution, right? Okay? One of the things, the chi-square distribution has a thing called degrees of freedom. Why do they call it degrees of freedom? I don't know. It's kind of a weird name. But your degrees of freedom, sometimes I abbreviate that df, equals the number of rows minus 1 times the number of columns minus 1. Okay? So, those are the two things you're going to need to remember. Now, I probably should let you know a little bit more about the chi-square distribution. So we're going to digress for a minute. So, so things to know. Things to know. Number one, the shape changes based on the degrees of freedom. And when I say it changes pretty dramatically. I'll show you that in just a minute. Number two, the distribution should come from a simple random sample. Okay? Number three, population should be normally distributed. Okay? All right, number four, if the expected counts are less than 5, and let's see, let me rewrite that. No more than 20% of the cells should be less than 5 on the expected counts. Okay? And number 5, no cells should be 0. Okay? All right, so let me just show you here really quickly. I'm going to find a chi-square distribution. Oh, actually, I'm going to add a 6th one here. It is not symmetric. Actually, I'm going to add another 7. It's always positive. Okay? Because we're squaring things, it's always going to be positive. Okay? So remember your t distribution, your z distribution, you can get negative values. Can't do that with this one. Okay? So let's talk about the chi-square distribution. Okay, let me share this with you. Okay. So this is an example of a chi-square distribution. For some reason, I don't know why they put the letter K there, but that's your degrees of freedom. So if you have a chi-square with 1 degree of freedom, it's this yellow line. It starts way up high, and then it goes down low like this. Does that look like a normal distribution to you? Not even close. 2 degrees of freedom is the green line right here, okay? If we go to 3 degrees of freedom, it's this light blue line. So rather than starting at the top, it starts at the bottom. It goes up and then it comes down. 4 degrees of freedom is the blue line. 6 degrees is the pink purple line. And then 9 degrees of freedom is the red line. This changes a lot, right? Not even close to symmetric. Okay? Does that make sense? All right. So, actually, I'm going to add another couple of rules here. Sorry, I'm giving you so many rules. Number 8, it's always, maybe I should put the alternative hypothesis is always a right tail test. Okay? And you'll see why in a minute. All right, so let's go back to here, and we'll go back to our problem. Okay? Come on. All right, so we're doing our chi-square. Okay, so just as a reminder, chi-square equals the observed minus the expected squared divided by the expected. Okay? All right, so here we are. We've got our third table here, the chi-square table. So we're going to take, and please use parentheses. This is another place people screw up. So use parentheses. It's going to be the observed 35 males were admitted, minus the expected, we only expected 31.5. We're going to square that number, and we're going to divide by the expected. Okay? Equals the observed minus the expected squared divided by the expected equals the observed minus the expected squared divided by the expected equals the observed minus the expected squared divided by the expected. Okay? Does that make sense? Okay? Now, you guys remember what this Greek letter is? It means the sum. Do you remember what it was called? Sigma. Sigma. So you just went straight for sum. Yes, it means sum. Okay? So I need to find the sum of this entire table. I'm going to click on my auto sum button. That's the Greek letter sigma right here. For those of you who are watching at home and didn't know what I was pointing at, I was pointing at that thing that looks kind of like an E, the Greek letter S. All right, so we're going to add up that sum. So so this 1.55, this is my chi-square statistic. Okay, that's the value. All those calculations to get that one value. That's what I'm looking for. Now let's talk about our degrees of freedom. Okay. How many rows do I have in my table? 2 rows. Minus 1 is 1. How many columns do I have? 2 columns minus 1 is? Multiply 1 times 1 and I get 1. Got 1 degree of freedom. So that would have been the yellow line on, oops, didn't mean to do that one. That's the yellow line. So that's basically this yellow line here is what I'm looking at. So we're going to reject if, so one way to think about this, well, we're going to reject if your sum is large. So I'm going to add that here because it'll make a little bit of sense. If the sum is large. Now let me ask you guys a question, okay? So if the expected numbers, so I'm going to change this for a second. So if I have 35 and I expected 35, that number is going to be very close to 0, right? And if I expected 20 and 40 and 45, okay, I would have a very small sum, right? Does that make sense? I'm going to erase that and go back to the way we were. Or let's pretend this was 70 and 10 and 5 and 55. Okay? Do you see how these sums are really big now? Okay? So if I've got a large sum, it's going to be, that's going to tell me there's a difference. And if I have a small sum, it's also tell me there's not a difference. So the question is 1.55 big or small? And I don't know yet. Okay? So we've just done step number 4. We found our chi-square test statistic, which happens to be 1.55. Here, I will put that here. After all the calculations, we got 1.55. Step number 5 is what? Find the p-value. Okay? Now, there's going to be 2 ways that we're going to do this. We're going to do this with the computer, and I think you're going to find that the computer is a lot easier than the chart. But Tuesday's quiz is going to be with the chart. Okay? So we'll use the chart. Okay? Now, if you were going to come up with a command for the p-value for the chi-square distribution, Robert, what would you call it?
Chi-square?
Oh, he said chi.
Chi-square?
Chi-square. Okay? And that's exactly chi-square. Okay, now. Oops. Now, I've got 2 choices. I've got a bunch of choices here, but we're going to use the chi-square dist. Do you think we want the right tail or the left tail?
Right.
We want the right tail because
It's always right.
it's always right for this test. Okay? And I'll explain that in a picture in just a minute. We're going to do the right-tailed test. Okay, what do I put in for x? Or chi? You can think of that as the chi. At 1.55. And how many degrees of freedom do I have?
1.
1 degree of freedom. So I'm going to get a p-value of 0.211. Okay? Now, how would we do this on the chart? Okay? So if you still have your old pink ones with the bad formulas, the chart's fine.
And
Okay.
this is a different chart too, right?
This is the newest chart that you haven't used up till today. Okay? So we're going to look at our chi-squared chart here. So here's our chi-square distribution. It's in purple or blue. I don't know. So it look blue or purple on
It
yours?
looks blue here.
Yeah, it's supposed to be purple. So our color laser isn't very good. But at any rate, okay, so here's the deal. Okay? So you can look at the 3. We're not going to focus on those other 2. We're just going to look at this one. We're doing a right-tailed test. Okay? I want my alpha to be, we forgot to identify our alpha. What was our alpha?
0.05.
That was the one number we forgot to do was 0.05. Okay? Because we didn't say, so it's 0.05. Okay, so the idea here is you've got your degrees of freedom in column B, and then this is the value to the right of that. So if I'm looking at this line, 1 degree of freedom, and I got a value of 1.55971, right? So where does 1.55 fit on this line here? You see? It fits right between those 2 numbers, 1.55. So if it fits in between those 2 numbers, it's in between those 2 numbers. Okay? So what we're going to say here in this case is it fits right in here. Okay? So my p-value, all you can say with the chart is it's in between 0.10 and 0.90. Okay? So you can't, so this is kind of like the T table, in that you can't get an exact value. If you want an exact value, it's going to be that. But with the chart, we'll just say it's between 10% and 90% essentially, which 21% is in between those 2. Okay? Step number 6 is reject or not. And the survey says what, Olivia?
That you should reject it.
Who agrees with her? 1. Who disagrees with her? You should have all disagreed with her. Do not reject. Okay, how do you know? Is my p-value low?
But it's not lower than our alpha.
Yeah, we're comparing this number to our alpha, which is 0.05, right? We'll compare those two numbers. I'll put them in orange. Okay? Is the p-value lower than my alpha? No. So do not reject. Do not reject. Okay? So therefore, step number 7 is what, Casey? Write the conclusion in English. And so the conclusion is
Would it be
if you do not reject, there is not enough evidence What does your null say? There's not enough evidence that gender is not independent of admission. Or to better answer the question, is it fair to conclude discrimination?
Yes.
No. There is not enough evidence of discrimination. Okay? Now, really quickly, who believes that? Because here's the thing. It looks like we got discrimination going on here, right? 10% higher admit rate for men than women. And we just said, no, that's not true. Is that a bunch of lies, damn lies, and statistics? Which one do you believe? Okay? So here's what happened. This actually happened at the University of California at Berkeley. And they said, we don't believe your stupid statistics question thing. And so here's what we're going to do. We're going to go, since we only have 2 departments, although they had a lot more than that, we're going to go to the engineering department, and we're going to go to the English department. We're going to see if there's discrimination. Okay? So they went to the engineering department, and they said, you know what? 30 men were admitted, 30 were denied. What's your admit rate? 50%. And they said 10 were admitted and 10 were denied. What's the admit rate for females? Also 50%.
Wait, why isn't it 0 if all the admitted got denied?
Because you got total, right? 60 people applied.
Oh, I understand now.
Okay. So we're taking the admit rate here divided by there. That's 50%. Okay. All right. So now they went over to the English department. They said, okay, let's find out. It must be the English department. Clearly, the engineering department is not discriminating. So they said 5 were admitted, 15 were denied, which means 20 people total were there, right? Okay, what's your admit rate? 25%. 5 divided by 20 is 25%. For the females, 10 were admitted, 30 were denied, total of 40 people, and the admit rate was also 25%. Okay, now here's the interesting thing that happened at Cal Berkeley. It actually turns out that there was discrimination going on, but it was it was backwards. Let's change this to 29 and 31. Okay, we'll leave that alone. So you can see that men were admitted at a lower rate than women. And over here, let's change that to 4 and 16. Okay, maybe we'll take that to 11 and 31. Okay. We'll change this one to 11 and 9. Okay. What happened here? Okay? So you can see that, yes, there was discrimination, but it was benefiting women. Women were being admitted at a higher rate in the engineering department and a higher rate in the English department. Okay? So this is what's known as Simpsons Paradox. And what that means is when groups are unequally sized, sometimes associations can reverse. How about that? Okay? So we can believe our original thing that said there is not enough evidence of discrimination. Okay? And in fact, when we look at here, oh, why did that do that? When you look here, the women were actually had it better than the men. But because this school is so much larger than this school overwhelms the overall numbers, which is why, in the first place, it looked like there was discrimination going on. But really, it was discrimination in the opposite direction. Okay? All right, you're going to ace my quiz on Tuesday.
Is it just on that?
It's on chapter 25. So I've already posted the homework. I'm actually going to post some Excel homework because I think you guys need practice. I will post this up as well. So this is your chi-square independence test. This is your Simpsons Paradox. Okay, so check that out. I will post it with the homework, just like I did with the last homework. And so that'll be due on Tuesday. Okay? So see you all on Tuesday. And good luck.